supposed to be done right when you came back from break, but you had last night as grace to keep working on hyperbolas. Okay, how did you guys graph y equals 9 minus x squared? Nothing?
Oh,
Up 9?
You up 9 and then down, like parabolas downwards.
How could you know where it hits on the x-axis? Couldn't we do old school? Couldn't we find the zeros? And so what are the x-intercepts going to be? When is it going to hit the x-axis? When x equals plus or minus 3. That might have helped a little bit. Because then you knew it was supposed to hit at 3. Now technically, it just says the first quadrant. So I've only drawn the first quadrant part of the parabola. It does technically go this direction, but I haven't drawn it. However, where am I revolving around? The y-axis. So did you guys show your little revolution arrow around the y-axis?
Yeah, could it have been on top?
Yeah, it could have been on top or on bottom. I wouldn't mind either way. As long as you have it around the y-axis. And then as you spin it, isn't it going to end up going to the other side as well? So even though it didn't say to graph the other side, technically you could have, because as you spin, what's in the first quadrant will go to what's in the second quadrant. And then they'll come back around again. And then we do have our little bell shape, paraboloid. As easy as it gets? Yeah, I guess so, for this section. So we saw yesterday ways of spinning hyperbolas, ways of spinning ellipses, and then ways of spinning parabolas. Now remember, kiddos, for a paraboloid, you don't necessarily need it to look gorgeous, you just need to show me some sort of spin. Does that make sense? You just need to show me some sort of spin. Whether you show necessarily the dotted behind, going back into the page and all that jazz, or whether you show me like the cool fun cross sections if you really want to. You don't have to do all that extra stuff. I just need to see the parabola with the spin. So do you guys see how this homework is going to help you review? What do you have to do first before you can ever spin it? Graph it. Yeah. Before you can ever spin it, you have to graph it. So, just because we're about to check section 10.4, let's talk about how to graph this hyperbola. What would you guys do? It's okay, I'm not leaving you alone on this one. I'm here. How do we graph a hyperbola? Let's review real quick.
You divide by 9.
Good. Divide everything by 9. Divide everything by 9. And what are we trying to get, or what are we trying to do? Wait a minute. Do you want the negative one coming first in the hyperbola? Remember in the hyperbolas we want everything equal to 1, like ellipses as well? Who else was absent yesterday because they came out from that? So we're trying to get it into that standard form that you just passed. We're trying to get our equation in that standard form so we can figure out our clues for our A's and our B's and our H's and our K's and all that jazz. So then, Austin, I'm going to write the positive one first. That's how we're used to seeing it. This is getting closer to our standard form of y minus k squared over a squared minus x minus h squared over b squared equals 1. What's our center? Good, our center is 0, 0 because we have no subtraction for the x or the y. So our h is 0, our k is 0. From that 0, 0, am I going to go up and down to my vertices or right and left to my vertices? It does say x equals 6 and negative 6 up here, that's true. But what term comes first in my hyperbola? Yeah, and whichever is the positive term, that's the way that shows the orientation of I need to go along the y's to get to my vertices. If the x term was first, I go along the x-axis to get to my vertices. So if we're doing our hyperbolas, we need to go up, we go up 9 and down 9? No, you just go up 3 and down 3, remember? It's what constant is being squared. So now I have my vertices. At 3 and negative 3, but if we wanted to write them out, just to review section 10.4, we could. Our vertices would be 0, 3, and 0, negative 3. What else do we define for hyperbolas? Foci? No, we're just graphing. Something we don't need foci. Asymptotes. Don't asymptotes show us how wide or how narrow our hyperbola needs to go? Yeah, it would be one. And the reason being is for the slopes of our asymptotes, we need to do m equals plus or minus both directions from the center. The coefficient under the y squared term, 15 squared, and the coefficient under the x squared, they do end up being the exact same thing. So it will just be plus or minus 1. Always the y one over the x one. Because just think rise over run. So now I can go ahead and show my asymptotes to be, let's see, approximately. And all of that was to get, I'm actually going to erase this in a second because the asymptotes are good, but they're going to be kind of messy for when we try to graph. So try to make them as light as I can. Alright, now we can go ahead and sketch our hyperbolas. So, when it says x equals 6 and negative 6, we're at 3 right now if we go ahead and plug in. So you keep on going to 4 and 5 and 6, 4 and 5 and 6, so that's how much we're going to extend out. So we're going to go, there we go, and then go, there we go. It's about right. This one's almost hitting that 6 mark here, almost hitting that 6 mark there. So remember when they tell us that negative 6 to 6, they're just telling us how far to extend out before we stop, because remember these are infinite figures in and of themselves. We need to stop them in order to be able to show that finite shape. Because where are we revolving this about? The y-axis? Oh, wait a minute. Hold on. Hyperbolas have how many branches?
2.
2. So we have to also get our downwards one. In this context, or in this problem, if it says go about the y-axis, is this its transverse axis or its conjugate axis? Transverse, good, because it's going through the hyperbolas. So you guys could memorize that it's going around the transverse, so it should be, is that a 1 sheet or a 2 sheet? Or maybe you can visualize and say, hey, if this was on a string, and if I spun, and if this would come out, and if this would rotate around, what would it form? 2 separate or 1 whole?
2 separate.
2 separate, 2 whole. This is going to be a 2 sheet. Remember, follow this revolution that you see down below.
Did you give examples of that?
No. We didn't have teachers meetings all these, so I couldn't see. Middle school teachers had a meeting this morning. Does anybody have wish out though?
I did.
Hey. Have you had it yet today?
How-
Perfect. Can you just ask him if he has the wire thing? The wire thing that I was trying to get involved in.
This is the.
Yeah.
Mr. Warren and I tried to put it together with Oxy, and it didn't work. It just doesn't work. So if we want to put it back together, we have to weld it.
I have to actually weld it. We'll have to ask Jose. I think Jose has a spot welder. This
Yes.
Thank you, Juju, for letting me know. I just grab it back and the last thing. Because they did spot welding on this thing, so they have holes in there. Alright. If you guys want, you can embellish. You can have fun with it. Some of you are, some of you are like, whatever, as long as it has something that kind of works and gets changed. But either way, we have our 2 sheets. Okay, so guys, I didn't give you the good idea of this homework, which you were supposed to finish last night, but you were supposed to start, or you could have started. Remember that this section, let's see, what's the title? 12.3a gets you from numbers 1 through 10. I think I have the homework written somewhere. There we go. So it can get you guys up through 10, although I think those numbers have changed a little bit. Does anybody have those circle numbers in front of you? It is 1, 3, 4, 5. I don't think you turned it. Oh, I did. What didn't I give you? Oh, I didn't give you 9. Let me cross that out real quick. I didn't give you guys 9. There we go. So, 12.3a gives you these problems. Okay? But what it doesn't get you is 11 and 13. And that's what we need to cover today. But first, let's very quickly talk about our evens from section 10.4. You guys do need your graphing calculators for the second half of 12.3. So make sure you get out your graphing calculators. Yeah, if you go quick. You're struggling. Did you miss it? Were you talking?
Yeah.
Alright, kiddos, the first few are matches. We're going really fast. Hyperbolas, it's been a while. Remember, we do have a test coming this Thursday. 12.3 is our last section, so we need to be reviewing all those formulas. I think I rattled them off yesterday in class. But sadly, after a break, we kind of have to be reviewing to get our brain back into the conic section-y mode. And that's what tomorrow's going to be. It's going to be a work day. We're going to be doing practice problems probably for pretty much the whole day. I'm going to really quickly say what's on the test. And then we're just going to be practicing, and I'll be available for questions if you guys have any. 6 is C. 8 is D. 10, was not matching, sorry. Number 10 ended up being finally simplified to be x squared over 16 minus y squared over 20 equals 1. My hint, remember one more time, whenever they give you clues at the beginning of a problem, my hint is to graph first. Try to get a feel for what type it is from the graph. And then match it with the standard form and plug in. Number 26, they gave you the equation. Here's a great example. You had an h, you had a k, which moved the center to negative 3, 2. You had a horizontal distance of 12 to get to the vertices on either side. The x term came first. We went out 12 to the vertices. They did go ahead and also find their foci, which would be a little bit further. They didn't actually show them on the graph, though, for whatever reason. That was kind of weird. But the asymptotes, to get the equation of the line, you plug in the point slope. You take the center, you take your negative 3, positive 2, and plug that into your h into your k. But to get the slope, we take the rise, the y coefficient, which is 5, and then over the run, the x coefficient, and that's where we got 5/12. So it went up 5 over 12. That's why this was, or the hyperbola branches were so narrow, was because the asymptotes were so high. That's a great, big hyperbola question to make sure you understand. Awesome. Well, you look to see which term for a hyperbola. Remember, which term comes first? The x term came first. So then, in the x direction or horizontal direction, we had to go out from the center. That coefficient, which would square root of 144, which would be 12. So from negative 3 to... Yeah, to the x's, we have to add 12 and subtract 12. So negative 3 plus 12, there's your negative 3 minus 12. So think if the x comes first, add, subtract from the x's. If the y comes first, add and subtract from the y's. Okay. Number 42 gave you clues again. I think out of all the kind section homework, this one is the trickiest in the sense that if you took your asymptotes, you would think that this was the y or the b1, and this was the x or the a1. You would just say 3 over 4 and try to plug in. The problem is 3 squared plus 4 squared does not equal 10 squared, so it doesn't match up. So we have to think, okay, the slope reduced to be 3 and 4, which means it could have been 6 and 8. It could have actually been 9 and 12. It could have been a lot of different things. But if you check 6 and 8, which also would make 3/4 when you divide, 6 squared plus 8 squared does end up being 100 or 10 squared, and so it matches with the foci they gave you. So then we can plug it into our formula with the, let's see, the foci were x's apart. So yeah, the x term comes first with its coefficient of 8, and the y term comes second with its coefficient of 6. That one I thought was the trickiest, because it looks like you know a and b, but it was really reduced from 6 and 8. We had to keep on going from there. The last ones, kiddos, they gave you standard forms, and you were just supposed to figure out what it looked like. I don't think any of these were degenerates, meaning what they looked like is what they actually were. So if you were to move this over and complete the square, you would end up with a 1 over here. You would not end up with a 0, so it would be okay. If all the constants cancel out, that's when it's degenerate. That's when it's not a conic section. But 54 is a circle because they're both squared, so it's not a parabola. And there's addition, so it's not a hyperbola. And if you complete the square, it's not degenerate. And number 56, only one of the variables is squared. That's a parabola. So when you try to simplify it, it's not degenerate. Number 62, both of these are squared. Hold on, there's a typo in this one. You guys find a typo? Is it minus 2x squared? Okay. It's minus 2x. The reason being is because I see down here that they said this was a -2. And it couldn't be a hyperbola unless there was subtraction. So they just did a quick typo there. So since they're both square terms, and since there is a subtraction between, and when you simplify completing square, it's not degenerate, then it is a hyperbola. And last but not least, 2 squared, both are positive. When you simplify, it's not degenerate, that has to be with us. The nice thing is, there are in the book, I guess, these little clues that you guys can memorize with A's times C's and what happens when it's equal to 0 or less than or greater than. That is a way of knowing for sure, without having to complete the square and see if they're degenerates or not. Without having or checking to see if maybe all the constants cancel out. So those little clues in the book, I didn't write them down, but they are good if you want to be able to know for sure. But the other nice thing is that you're able to know without having to complete the square all the way. But if we wanted to graph, of course, we would complete the square because it makes everything easier. 12.3 we're not done with yet, so let's go ahead and get rid of that. Tomorrow we do have a work day, so if you guys have any hyperbola questions, just bring it tomorrow. We can look at them. Chapel was yesterday.
Usually wait a day.
Yeah, usually, but not this time. I think because they had a special group coming. Alright, calculators out open. Today we're going to start with 2D and then we're going to go to 3D of a very particular type of question. And it's only 11 and 13 in homework.
Is this on the
There may be one of these on the test. And I try to be precise with how I graph all this. And technically, kiddos, I do have some of these things. I've already put them in a calculator and I kind of dragged the pictures over so that way we already have it, so you guys can see it. But then hopefully we'll also get to an example where you can use your calculator yourself. Let's go back. Long story short, inscribed figures. You guys have seen this since, I don't know, geometry, I think, where there was a figure inside of another figure. You have the inscribed and the circumscribed, the circles inside like squares or outside. You guys have seen them on SAT map that been down them. The calculus kids actually just had a problem that kind of involved this morning with ratio, but shows up every now and then. And the long story short of inscribed figures is maybe not all of their vertices, but at least some of their vertices are going to be located on the outer boundaries of another shape. Usually all, but every now and then, depending on the boundaries. They have different boundaries, their vertices might be in different places, but they have to have at least some vertices on the outer boundary of another. If we're talking about two-dimensional shapes, one inside of another, an inscribed figure two-dimensionally inside of another, then we're going to be talking specifically about the idea of area. The two-dimensional measurement is area. And this is an example of the type of question you might see. What is the maximum area of a rectangle inscribed within, and then they give us an equation. I know you guys are right. I'll give you guys a couple seconds. But as you catch up to this equation, I want you guys to think about, okay, we just in homework 10-4 saw the last 4 questions, I think, were all, here's an equation, what kind of section should it go with? I want you guys to ask yourself this question in this problem. 64x squared plus 25y squared equals 1600. Which conic section would this equation seem to be showing? Not a circle. An ellipse. Why an ellipse and not a circle? It has an x squared, it has a y squared, but what's true about the coefficients? They're different. A circle, it should be the same. For an ellipse, they're going to be different. So when I go ahead and divide both sides by 1600, and also this was the question you asked earlier. We're trying to get it in that standard form to help us out. 25 into 1600, how many quarters are in $16? Is that 60? Double checking the calculators. But if that's true, then we could say this one, 64 and 1600, it worked. Is 25. And here's another indicator. If it was a circle, once again, these should be the same. Because it would be the same distance out from the center when you're going horizontally and vertically. Since they're different, then it's not the same. But one key that's thrown into this equation is they say only y greater than 0. So down here in my graph, first of all, you see a limitation of your graphing calculator. Because this totally looks like, oh hey, it's kind of half of an ellipse, but it doesn't quite go all the way down. Problem is it does go all the way down, just your calculator with the pixels is limited. We talked about this a little bit at the beginning of the end with the graphing calculator handbook. With pixels, it can only keep extending so far until the pixel would make it go over the boundary, and so it just stops and it cuts off. Some of the newer ones with like the light up and the color screen, that might graph it a little bit nicer. But if you were to graph this in your calculator, y is only the top of the ellipse graph here. Yeah, y is greater than 0. So 1, 2, 3, 4, 5. We're going horizontally 5, as is seen in our little term up here above. The x coefficient is 5, 5 squared. And the y coefficient, how tall is this? 1, 2, 3, 4, 5, 6, 7, 8. As indicated by the coefficient underneath the y squared. Now, so far this is kind of just old school conic sections, because if we were to finish the whole ellipse, we would just go down 8, we go left 5, and we would just connect it. No big deal. We have an ellipse. They said y is greater than 0. We just have half of an ellipse. But what do they want inside the ellipse?
Rectangle.
Okay. Well, what kind of rectangle can I put inside this ellipse, kiddos?
Square looking one.
A square-looking one? Okay, that's true. The question, is that the only kind of rectangle I can fit in? Could I do like a really wide, narrow rectangle that would still technically be inscribed? Yeah. How about a really tall rectangle? I can fit all sorts of different rectangles in. So here's the dilemma. What are they actually asking me? Oh, so I have to find all the different possible ones and find all their areas and see which one wins? No, that would be horribly non-mathematical. I mean, it's experimental, I suppose. But how many rectangles do you think we could actually inscribe within? Infinitely many, because we can make these like just decimals apart.
This one looks good.
No, because we're not going to do that. So instead of doing all the tons of different rectangles, we're just going to choose one. Now guys, just because we choose one doesn't mean it's the right answer. We're just going to use it as a representative rectangle. Meaning there can be tons of different ones drawn. We're just going to use one. And here's what we're going to use from that one. We're going to highlight the point on the right where it hits the curve, and we're going to say, hey, I don't know what point that is because I don't even know if you're the right one. But the right rectangle is going to hit add an x and add a y. It's going to hit add an x and add a y of the outer figure, which some of you might have gotten just a little bit lost as to how I could have gotten this in my calculator. Kiddos, how could I have graphed this function in my calculator? Give the y by itself. So I would have ended up having 1600 minus 64x squared, only the positive square root, not plus or minus. Because remember, in circles or ellipses, the plus or minus, the positive is the top half, and the negative square root would be the bottom half. So just the positive square root. What did I forget? I didn't divide by what? 25. All under one big square root. So then I can say, okay, this box, this rectangle, whichever is the right one, which I don't know which is the right one, so I'm not going to go measuring and trying to figure things out. The right one is going to hit add an x, add a y. Now here's the dilemma that we need to go ahead and figure out past this point. We need to say our goal is to find the maximum area. So to find the maximum area, well, we somehow have to talk about area. So think about a rectangle, kiddos. What's the area formula, just like in geometry, for a rectangle? Base times height or length times width, same thing. Base times height. Almost. We can't just plug in and just plug in the y.
Oh, 2x plus y.
We have to think about up here, yeah, you're getting a lot closer. We have to think about exactly what would measure the base and what would measure the height. Now, the base, isn't x a horizontal measure, guys? If x is a horizontal measure, does it measure the entire base or just part of it? Yeah, the x just measures half of it. Because for any point you go over an x and you go up a y, right? For any point you go over an x and up a y. But guys, for the base of my rectangle, what do I actually need? Half of the base or the whole base? So how am I going to get the whole base?
2x.
I'm going to double it. Now, how many y's do I need for a height?
Just one.
Oh, just one. Because check it out. 1y is the height of the rectangle, so that's going to work. My 1x wasn't enough for the base, so I had to double it in order to be the entire base. My 1y is enough for the height. Ricky, I know it's hard. Yes. So now I have my area equals to 2xy. Okay. Now we want to find the maximum of this. We want to maximize. It's technically a snazzy word called optimization. We've talked about it a couple of times this year. If we want to find the max, what better than to use, hey guys, check it out. What am I trying to show you in this graph over here? What can your calculator do? Find the maximum, right? And this one doesn't show the cursor because it was blinking. But I found a maximum, but wait a minute, hold on. To do that, don't you have to have some function to put into your calculator? How do I take this area formula and how do I get it to be an equation I can put into my calculator? There's way too many variables going on. Figure out what about the variable. What do we know about y? What do we know about y? He's that whole shabam. He's that whole shabam up above. So I can actually take my area formula and I can say, okay, 2 times x, and I have my y. Go take that big old y expression and plug it in. Big old nasty 1600 minus 64x squared all over 25. Now, when we go to graph this, let me get my graphing calculator out. When we go to graph this function, do you think the window is going to just magically be nice for us?
Yes.
Really? Windows are nasty, right? The hope is that it would work out, but if I go ahead and plug in alpha y equals, I get my nice little fraction, so I don't mess things up. I have my 1600 minus 64x squared all over 25. Most of us start in a Zoom standard, but how's that turning out? Can I do a maximum feature on my calculator if I can't see it? No. So then, what's an idea? Austin, what would you do? Zoom fit? Is that 0?
Yeah.
Oh, hey, this one time Zoom fit actually does work really well, so it's never bad to try in the beginning. David, I'm still looking at you. Thanks. So, Zoom fit. Do you guys see where I got this graph over here? Same thing, right? Now, when we go to find the maximum, remember, second trace, and then we can go ahead and use, is it number 5? Nope, number 4. How do we answer these questions on our graphing calculator videos when they ask for the left hand? You go to the left of the maximum that you're trying to find, right? And so my left, oh, I am on the left. I'm like, yeah, on the left. That works. Enter. Then I need to answer on the right and go on the other side. So the long story short is we have to take some time in order to think about the area formula of a rectangle, to think about how to use our x's and our y's. That's the same maximum I found over here. How to use our x's and our y's in order to plug into that area formula, which you see right here. What's the shape we're putting in? How do I translate base and height in terms of x's and y's? Solve for y in the original conic section and plug that in. That's going to restrict, that's going to bound my graph. And then just use your graphing calculator. Because we don't know calculus. If we did, we could actually find this special vertex. It's not a parabola. We would actually call it a critical number in calculus. But we could find it with math. But for right now, since we can't, since we don't know those procedures to do, we'll just graph it and say, come on, calculator, help me out. And when you find this maximum, the last step is you just have to figure out what are you answering. What goes where? Which number is which? What do you guys think? What is the maximum area that this rectangle can actually have from those values over there?
283.2.
No. Too big.
Oh, 2 times 3.
2
times 4.
See, that's right.
Yeah, I see what you guys are trying to do. You're trying to plug in stuff. Question. Who is the y symbolizing if this is what I put into my calculator?
There we go.
Yeah. When I put this in my calculator, it's y equals, right? So I let y1, this is really y1. I pretended as though y1 was a. So when that point came out, that wasn't giving me the y for this original picture. It was giving me what I put into it, which is area. So how would I answer the area question? With what they said area was, the y value. And how do I answer the at, or the when, or the such that? I choose the x. And the nice thing is the x is the same, because when it says x down here, it's actually talking about what variable I put in, and I did put in an x, so it matches. The problem was with the y's, the y was actually symbolic of area. So I can say at or when x equals 3.536, I guess. And we could find the y if we wanted to. We would have to plug into our big old nasty equation working with above. So we'd have to use our 1600 minus 64 times 3.5355 or something like that. So long story short, we could have found a y if we needed to, but we needed to make sure that we could interpret the point first. And the point gives us an area and gives us an x value. And that would be the perfect rectangle or the biggest rectangle that we could possibly make. 3.536. Let's see if any of ours were close. There's 1, there's 2, there's 3, 3.5. Oh, that's almost the one that I drew just by chance, but I didn't need to. But this is a bit more precise. Now, with all of that, let me show you guys the steps to what we just did. Let me show you guys the steps to what we just did. You don't necessarily have to write them down. You don't necessarily have to memorize. Then you don't necessarily have to explain, like in sentences or in words, what you do when you do it. But I just want to make sure that real quickly you have like a brief overview of what we just did. We drew a picture. We figured out the inside figure. And we tried to label its dimensions with x's and y's. That's when we made the base the 2x and the height the y. We were trying to put its dimensions in terms of x's and y's. Then we figured out the area formula that we were supposed to be using, base times height, and we plugged in. But when we plugged in, we had a 2x and a y. We had too many variables, so we had to go back in our problem and say, hold on, wait a minute, who is y in terms of x? So we had to go find where we had gotten y by itself. Take that expression, plug in, so that way I have an expression for the last problem area just in terms of x. Then you plug that area into your calculator. You can find the max or the min using the second trace statement. And then it's just how do you interpret what you get? How do you interpret what you get? Technically, if you guys want to know why calculus kids talk about clues, it mostly comes up right here because it's really easy to forget about. Both what you're supposed to be doing and what you can be using to plug in. Because problems get long and kind of involved and you forget what's the objective versus what are just the clues that need to be plugged in. So hopefully you're going to get an equation in terms of x's and y's, too many variables. Go looking for a clue, go looking for some extra piece of information. It's going to be your conic section. Solve for y, plug it in, and you're good to go to your calculator. Now, this will be online if you want it. I wanted to go ahead and do one more example, because this is a hard idea, and the more practice, the better. This is your number 14, I think, in your worksheet, and we're doing number 13, or you guys are doing number 13 for homework. And I definitely shortened whatever the directions were. I think it's like a whole paragraph. Woo, look at that. Woo. Anyway. The ellipse x squared plus 4y squared equals 4 is rotated about the x-axis to form an ellipsoid. A cylinder is inscribed in the ellipsoid with its axis along the x-axis. The right base touches the ellipse at a sample point xy. Sketch the ellipsoid and the cylinder. Plot the volume as a function of x. Sketch the graph. Find the x that maximizes the volume. And find the maximum volume. Yeah. I know, there's a lot going on. This mostly has to do with your number 13 and kind of the number 17 bonus. Remember that we talked about yesterday. But if you were to graph this ellipse, you'd want it to look nice and pretty, so you'd want it to be all simplified. Have x squared over 4 plus y squared over 1 equals 1, which means we're going out 2 on the x, up 1, down 1 on the y, thinking about our major and our minor. And when it says this is rotated about the x-axis, then we would go ahead and make this an ellipsoid, which they talk about in the problem. Remember, this is the pill one. Like the day pool and the night pool. That's just what's on my mind. But then they're like, hey, by the way, there's a cylinder inside. Like, you have to be kidding me. There's a cylinder?
I'm not seeing the cylinder inside.
Seems like a cylinder inside.
That's so weird.
And then it gets a little crazy because you have volume equals pi r squared h. As you guys know, I'm going to go ahead and plug in x's and y's so it'll be saved online. If you guys want to see the rest of the three-dimensional power for it, I guys see this. Alright, Sarah, you are so perfect today. Yourself? Is that
You know what I mean? How did I show up? How did
Eileen, can you take this? Main office. Sorry.
Can I run to the restroom and see?
Yeah.
Oh, no longer doing it.